All right. I struggled for a while last time on one particular problem, but a kind person who I guess is either far better at this coding than I am, or far better at reading the actual problem than I, left information in the comment section of my last video. So that highlighted what I was doing wrong. Basically, so if you didn't watch the last video, you have no idea what I'm talking about, but basically, last time I was kind of very upset because I was getting all the right answers, but I was still getting errors that I was unable to diagnose. And I thought it was some size error, and this all seemed to be right, but it turns out this is actually should be a -1, and this is because each of these polynomials, this zero term, you can see in the matrix here, the zero term is all just has no exponent. Well, it's to the 0th power, I guess. So when you're doing this length out, you're subtracting 1 from each of these, and then you're adding 1 back. So so it's -2 plus 1 gives you -1, and that's the correct answer. I should be honest, I did check this was the correct answer before submitting it. I wasn't going to make a video of me sitting for another hour trying to figure it out, but yes, this took me 1 second to do and check, and this is right. So we'll just move on, I guess. Now I have the will and motivation to do it again, now that the problem has been solved. So we can move on to the next section where we're talking about the Fourier transform and the quantum version. I should note that although I stand by my criticisms of the error communication in the coding sections, I admit that I'm not necessarily the target person because I don't usually read all this stuff, you know. So yeah, which is just maybe if you read everything over here to read everything over here, it's probably easier, but still, I stand by the error communication point. See right here, I know that, well, I don't want to return anything. I know that the Hadamard is the 1-qubit Fourier transform. That's just something that I know. You can look and see that here omega is n is 2 to the n. So that is, in this case, n is 2, right? So this is oh, sorry, big N is 2, so little n is 1. So over here we have omega equals 2 pi I over 2, which cancels out, and e to the I pi, of course, is -1. That's what some people call the most beautiful equation in math, I think. Most beautiful math. See, make sure I'm not making this up. Wow, this so many ads. Okay, maybe I am making this up. Oh, no, I'm not making it up. Here we go. See, so e to the I pi equals -1. And so that's just a Hadamard, 1, 1, 1, -1, 1 over the square root of 2. That's Hadamard. Oh, I have to measure it. Oopsies. There we go. Oh, we have to do the matrix. Okay, well, maybe I'll see if I can automate this a little. Maybe I don't feel okay now. W of n turn and by the exponent of 2 times y times 1j over n. So then we have our matrix is I'm just thinking n is 4 in this case, right? Yeah. So we'll have the 4x4 matrix. So we'll do for I in range 4. We have I'm just thinking if this is the easiest way to do it. Probably not. Yeah, I'll just do it this way. U equals 1, 1, 1, 1. Then we have our second row, which is 1. W of 1, 2, oh, sorry. Yeah. W of 4. Then we have our 1, W of 2, W of 4, W of 8. See, n is. Oh, no, it should be 3. I'm trying to do this quickly and it's not going. 2 times n minus 1 is 6. Okay. Now we have of n minus 1, which is 3. W of 2 times n minus 1, which is 6. And we have W of n minus 1 squared, 9. Okay. All right. You get unitary U. I have to return the state. Yes, I do. Oh, did I not write it down correctly? Let me look up, make sure. I'm just not messing up the equation. 246, 369. Right, this is the matrix we want right here. This 4x4. Oh, I realized what I did. I forgot to do 1 over numpy dot square root of 2. No, sorry, square root of 4, which is just 1/2. There we go. Okay, that's not right either. Let's see, we have this. This matrix is what we want here. We have, let's see, 1, 1, 1, 1, 1, 1, 1, 1, W, W2. Oh, I see what I did wrong. Okay, I think this should be 4. Yeah, so the problem was W is in the, this is the base case. I was changing this in every time. There we go. All right. Oh, this is telling us what to do. The last term from right to left. Let's see, sorry, I just got a notification. Right to left, right. So we have Hadamard on I. Second qubit. Second qubit and first qubit. And then we have this is the controlled S gate. So we want to do Hadamard on the one. I don't know. I don't remember what the controlled gate is. Let's see. I want the controlled S gate is what I'm looking for. I remember there's like a CRTL or something. I'm not going crazy, am I? Yeah, I know. I don't know. You see, this is where it's like the documentation isn't great because this is clearly what I wanted. But CRTL control equals 1. Okay. CRTL UML.s control equals 0. Assume that means the target is, oh, I have to put, there we go. And then we do UML.add 0. And do return UML.state. All right. CRTL, oh, CTRL. Okay. Did I swap these on accident? That's possible. No, I did not. Okay, what am I doing wrong here? Oh, right. Then we need to swap. We have our swap is all caps. Oh, no, is it the swap gate that we want? Let's see. Let's see. Let's take a peek at the hints. Yes, we use CTRL. Okay, so we have this is H1, H2. Right, this is the Hadamard on H1, this is Hadamard on H2. Here and here. This is the controlled S gate. Let me check what swap does. So if we have swap is 1, so it's going to do row times column, right? Yeah, so it's going to row times this column is 1, row times this column. Yeah, these are all 1, so it's going to do nothing here. I should just do I don't think the swap is doing what I want it to do because it's swapping the state of the qubits, which is not the same as swapping the inner rows. I don't have like an intuition for what swapping the inner rows even means. Let's see. Let's see what let's see what happens if we do this matrix multiplication. So we have our 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, right? That's our swap. And then we have our, doesn't matter, I'm just leaving out the constant, 1, 1, 1, 1, 1. Then we have our 1, negative 1, negative 1, 1, negative 1. We have our 1i, 1i, 1, negative I. And then we have our 1, negative I, negative 1. All right. Does that swap these two rows? Let's see, we have, so our desired matrix is 1, 1, 1, 1, 1, I, negative 1, negative I, 1, negative 1, 1, negative 1, 1, negative I, negative 1, I. Okay, that seems to be what I thought it would be, but oh, did I? Oh, yes, I think I'm doing this in the wrong order. It should be 0 and then 1. Oh, no. Okay, so what's going on here? Let me see. We apply these operations from right to left. So that's Hadamard on qubit 0. Controlled S gate. Oh, I see. I think I know what the problem is. See, yeah, that was the problem. I was, this is the controlled unitary structure, but this is a swapped, right? This is qubit 0 and this is qubit 1, whereas I was reading this. It's that position. So there we go, 2 qubit Fourier transform. I guess it also just tells you the answer right here. So I guess that would be easy as well. All right, connecting the dots. Let's see. Yeah, so we have our Hadamard and then controlled rotations, Hadamard controlled rotations all the way down. And then swaps. You'll sometimes see it with swaps, sometimes you'll see it without swaps. It doesn't matter. It's just sort of for positional representation. Oh, I know what let me look at what the phase gate is in this system. What's parametric? Let's see. Phase shift. That's what I want. E to the I. Okay. So this is the circuit we're doing. So we have 0, so this is e to the I phi, and we want our exponent to be phi here is 2 pi I over 2 to the k. This is, so we want 2 pi over 2k, 2 to the k, 3 times I over 2 to k. In this case, k is 2 equals 0. We'll copy this and paste it down, just shifting the control and shifting this to be 3. And then we will do wires 1, paste this again. This time we need to say wires equals 1, and control is 2, and then we will do the add one. Return the state. There we go. Oh, something didn't go quite right. Let me double check everything. All right, so we have R2 equals 2 pi I over equals I pi over 2, which would be 2 times pi over 4 is pi over 2. 2 to the third is 8. So this would be, yeah, this seems correct. Control. Oh, I forgot the swap. Oh, what else am I missing? Hadamard. Controlled R2, controlled R3, controlled R2, controlled R3, controlled by 1 and 2, Hadamard, controlled R2, Hadamard, swap. What's going on here? Why is this wrong? Let's see. Let me see what's going on here. So this is the circuit we want. Something I'm just mistyped something probably. Let me check the phase shift gate. So this should be, maybe I'll just type it out explicitly. Maybe something weird is going on in that calculation. Oh, there we go. Okay, now it seems to be right. What's going on here? This is the gate that we want. All right, let's just stay focused and get this. I pi over 2, I pi over 4, which is exactly what we have. We have this controlled, we do swap. I'm not sure what's going on here. Let's see if there's anything on the... Let's see if there's anything on here. We're on F3. Nope, nothing. Okay. All right, what am I mistyping? Because this is the circuit right here, right? We have our 1, 2, 3, 4, 5, 6, 7 gates. 1, 2, 3, 4, 5, 6, 7 gates. Just make something's going on here. I'm just making sure I'm not missing something obvious. We have 3 wires. We have our Hadamard on our first wire, or wire 0. We do controlled R2, controlled phase shift, which is the exact gate that we want. Let me R4. How odd. Very odd indeed. I guess I will have to do the dreaded actually use my own code. So let's open up the test file. Import any lane as QML. All right, then I will do okay, I'm just comparing it because I know there's a built-in Fourier transform in penny lane, so I'm just gonna check UML.QFT is what I think it is. Check. See, I'll just check first. The qubit QFT 0. Let me see if I can just. All right. I will now copy everything over. So I will now share this. Hold on. We'll close. Okay, I will now share the screen. And I do see that there is in fact an error, so something's weird is going on here. Let me add this. There we go. Let me add this. There we go. Let me shrink this down to size. There we go. So you can see I just copied my my code over, and let me check, just make sure that penny lane. I'm just checking to make sure that I'm like 99% sure there's a penny lane implementation of QFT. See, this is why it's annoying, because I look up QFT penny lane and it doesn't come up, which is very inconvenient, right? Like, how am I supposed to find anything if I can't? All right, now I found it. See, applies the Fourier transform. Does it do the swap? All right. Yes, I think this is what we want. So then if I go over, I can, let me do one thing, actually, let me do. There we go. All right, now we can see this code. So we can see the differences already, that this, the right side is the real, the left side is not real. So what I'm checking is what's going on here exactly. Maybe the phase gate is not what I think it is. That's the only thing I can think of right now is, right, that's the, assuming the phase gate is what I think it is, that's the exact circuit, but maybe there's a different gate I should be using. Let me check. Qiskit has some good info on the Fourier transform, so I was just checking what their gates are like. Let's see. Let's get CP gate. Let's see. Qiskit gates. All right, yeah, I think this is I think this is what we want. But let's see. If I go to this implementation, I can see that they have the Hadamard and then the two. I mean, of course, they have it reversed because it's in Qiskit, but this still seems like the same. Yeah, this seems like what we want to do. Let me check what the QFT operation. I just realized you can actually look at what I'm doing, what the QFT operation is doing in the source code. Hey, that's what I did. That was my implementation. Let's see. Maybe it would be helpful to see the matrix. Let me go over to my code and then see line op. Okay, and then here I'll show this, I guess. So we have our op, and then we do op. Or how do I get the matrix? I forget. Let me look up how to do this. How do I just want, let's see, reading the unitary of a circuit. Oh, no, you can't do that? Oh, I thought there was a way to do that. That's very sad. There's no way that you can get the unitary from this code. So what we can do, however, is we can do this very easily. We can say, well, not very easily, but easily enough that we can do equals Hadamard matrix. So we want this. We actually want to do this again because we have two. And then we want this. Let's see if this even works actually. No, it doesn't. Never mind, that's not the best approach. I was just going to write out all the matrices and multiply them. Which I guess I can do, but let me go back to the Qiskit reference again. This is funny, right? There's certain irony in trying to solve their problem by using Kisket's documentation and textbooks. See, this is why it's happening again. Oh no. This is why I'm confused, right? It's because it seems. Let me try another basis input. Like 5 and 5. Let's see. Yeah, this is very interesting. Okay. Okay. Actually, here I can go to. Let's actually look at this. Because I remember, I know I've made a previous video on this for those of you curious what this is. But also I know the documentation, here we go, has examples, pretty sure, of the 3-qubit. No, I was wrong. So we'll just do 3-qubit. Let's take a look at this. Something's going on here and I'm going to figure it out. Let's see. Make sure I'm sharing. Yes, I'm sharing the right screen. I just got an insane amount of notifications again. Okay, yeah, I don't need to know about the roots of unity. I just want to see this sort of too theory focused. Let me look at some. Let me see. So this implementation, right, if we swap them, put x1 up here, then we have no, that doesn't make sense. Let's see. Yeah, see, this is the circuit that we have here. Then we have swaps. Let me see. I guess I'll just try out different things. That's all we can do. Let's see, what are we at? 44 minutes. Okay. No, I'm gonna get this. I'm not gonna give up. So the problem is that this isn't right. And it's not right. Let me actually. Let me try something. No, that's a lot of work to try this in a different framework. Let me just try one thing. Let me see. I go over here. No, I'm gonna get this. Don't worry. I swear this is how I've done the Fourier transform. Okay, let me actually go. Like I've done it in classes before, and I feel like this is just something I'm missing in the penny lane experience. Let me see. Fourier transform. Right, like something. This is just objectively what's going on, right? We're doing the Adamard. We're doing here. I guess. Okay, I didn't want to do it, but we're doing it by hand. So here's what we're gonna do. We're gonna go over here, even though I do not want to do this. You can see. We're going to go here and we're going to say we're just going to actually here's what I'm going to do. I'm going to check the 2-qubit case first. I'm going to see if the 2-qubit case is right. Let's just we can have the third wire. That's fine. But I'm just going to check the 2-qubit case first. Now let's try 0. Okay, I'm just going to see, right, and see what happens. Okay, so there's some the 2-qubit case is not correct. This is smart. I should have started with this. The 2-qubit case is not correct. Okay. I can adjust. It's kind of a pain to go back and forth, but you can see this is the 2-qubit case. The problem is there's some complex number here in the left side that shouldn't actually be there. So let's go and investigate this. I'm just going to try some stuff out. See what it yields. Yeah, I don't know. Okay. So something's going on. I mean, you can't see me rapidly rapidly switching back and forth between the execution and stuff. But let me now go over to what I know. I know for a fact that there's 2-qubit quantum circuit opt. F1 and Fourier transform. So let's look down here. And we can, this is one we can definitely do. So we have, oh, did I forget the swap? Maybe. Let me see. Okay, yeah, so this is not, oh, I wanted this to be, this is not right. Somehow, I think their implementation of phase gate is messed up somehow and converting local phases out or something, because this is definitely, okay, I'll do it. I'll do this. I'll do this out. So we have our, I'll do this, hold on. We have our H1, our H0 equals matrix divided by 4. We have our H1 equals the Kronecker of 4 matrix. Okay, and then for this middle section, right, we have our controlled phase shift. So we have our SC. We have our on the first qubit, we have our identity, or sorry, our phase gate, which I'm checking the matrix for right now. So if we have this, we have our matrix. Yes, here we go. So we have our, what I wanted to do is we have our Y4 see, state 1, 1, 0. This is the outer product of so now we have our, let me see if I can just do phase shift matrix. Let me see what happens if I do this print x. Let me see, can I do this one? Property. Okay, that's fine. Okay. There we go. This is what we want. Let me see, can I do, does this work? Let's see if I copy this. No, it doesn't work. Okay, so that's fine. So then we have our phase shift here, which is X. So we want to do X comma, outer, I guess, or I can do it array, and then the outer product, which is 0, 1, 0, 1, should be 0, 0, oh, this needs to be 0, 0, 1. There we go. let's do is equals, we're doing 0. Array. We have our 1, 0, 0, 0 state. We have result equals map mul of our 0 on our initial state. We have our, then we have our C on this state. Then we have our H1 on this state. And now I will test this. Oh. Somewhere I am messing up. Oh, this should be numpy of I of 2. That's my bad. Oh, let's see. I'm just messing with the state somewhere. Let me just double check. H0 dot. Oh, that's why I keep messing this up. It should all be 2. Okay. Okay. Am I sharing that? Yes, I am. So what I get out here is 5.5 across the board, which is exactly what the correct answer is. 0.5, 0.5, 0.5, 0.5. So something. Wow, this is crazy, actually. So I just did the quantum simulation by hand, and I can now confirm that this is not doing what it should. Okay, let me show you what's going on here. So let me go over here. So what we have here is I have taken, okay, here we are. So I've taken the 2-qubit example, and I've said, okay, we're comparing it to the real one, which we just did. And then I'm saying, okay, take the Hadamard, right? We get the matrix. We're just doing the Kronecker product. So we do, here I can undo the swap, I guess, for a more fair comparison. It doesn't change anything. Get the phase shift matrix. We're doing wires equals 0. So we have this matrix, right? Which is basically exactly what we did before. And this is exactly what I'm doing. I'm multiplying the initial state, which is 0 in this case, the basis state. Oh my God. Let me just, let me try something real quick. I'm going to be so sad if this is the case. Actually, yeah, let me just check this real quick. Yeah, that doesn't change anything. Let me just check what the state is here. Yeah, so it's all in the one. It's all in the one space. So this is, something is not, right? This, I assume the Hadamard's work. I have no reason to believe that they wouldn't. This is the exact, oh, here, I'll even put a space in so you can really believe me. You can see my syntax code editor highlighting this. This is exactly what I'm doing in this operation, and then I'm just using the same, this is the same equation that they gave us before, remember, where we had this controlled operation, right, where we had the Kronecker product of the identity and the 0, 0 and the Kronecker of the target or gate, right, and the one state. So this is something has to be, right, like I have to be misinterpreting what the controlled operation is doing, because simply put, this isn't it, right? I just did the operation because I thought I was going crazy over here. I've done Fourier transforms before. How is this wrong? So something, let's go back. We'll take a look at the documentation and see something that is going on here, because something has to be going on. See, this is why I'm concerned, is that in the back end, it's actually implemented as RZ, right? Because if you do a controlled rotation of RZ, it won't work, because the RZ gate is the same as these two gates are identical, right? Up to this global phase, which doesn't matter in the single qubit case, but definitely matters in the controlled case. So I wonder, and I'm going to go check and see if there's a CP, a controlled phase gate. So it would be, oh my gosh, is it really this? Is this, okay, I'm going to try the C phase, which also excellent documentation. Control phase. Okay, check. Control phase shift. Okay, so I'm going to do control phase shift wires equals 0. Let's try this out. Okay, it did not work. Let me try something. Let me just. Okay, so I'm now using a controlled phase shift. Let me check one thing. Okay, I have now updated my code. So yeah, because I was worried that there's some problem with how the control operation is implemented. So I've now changed my code to use this controlled phase shift. I also updated my do-it-yourself. I also got rid of the extra qubit, so everything is just on this 2-qubit example. And this is, right, this is definitely let me see if I can. All right, so I'm getting the right results in the simulator. Let me check what's going on, because something weird is definitely happening here. Okay, so this is just, once again, this time I'm not confused by the errors. I'm confused by why this isn't matching up what the simulator does. So I'm just gonna do, let me just try something real quick. Oh my God. Okay. Here's what's going on. And this is truly, I don't know what's going on right now. I think I've confused myself successfully. But I'm going to move back over here. I was able to successfully submit it by just replacing this controlled thing, the CTRL, with the controlled phase shifts, which does, I think, prove my point that the way the phase shift gate works is not what you would expect, right? You would expect it to be phase shift. You would not expect it to be implemented as a constant times RZ, because that constant, or that global phase, would become a local phase if you're doing a controlled operation, which would have weird interactions. So I think that's what happened, which would be bewildering that they made that design choice. But I could be wrong, and that's very possible. But I still don't understand why this isn't anything. I don't know what their quantum Fourier transform is doing, because, or what this version is doing, right? Because this should be the actual quantum Fourier transform. Like this should, like if I, do this out, this is what I'm doing, right? This is exactly what's going on. I mean, you can have the swap or you cannot have the swap. It doesn't matter because the states are the same in the example I gave. But like, what is going on? This is, wow. This is so, once again, wild. Okay, what are we doing? Okay, we're swapping bits. Let's see, so we're gonna do for I age floor of and qubits over 2. That's going to round us down, so then we can do, we want to swap here's what we can do. I equals 0, j equals n qubits minus 1. This is probably the more naive approach. Now I not equal to j. Now dot swap. Wires equal I equal j I plus equals 1, j minus equals 1. And less than j. Make sure that that should be good. There we go. Yeah. Implement a circuit that performs. Okay. Oh, okay. So what we want to do is we want to say QFT rotations we want to do for I and range in qubits. QML dot higher is equal 0 I or j in range I and I plus 1 in qubits. Then we want to do QML dot for phase shift of 2 times 1 pi over 2 to the let's see, this was a difference of this is R2 and the difference is 1. This is R3, so I minus j plus 1. To the I minus j plus 1. All right. Oh, right. There's equals. Not quite right. Let's see. So we have. Let's copy this over. We might as well test this since we have this all set up already. Let's see. Can I draw this circuit? Let's find out. Oh, I need swap bits. I forgot about that. I forget how to draw things and you have the let's see. Okay, this is also another annoying. Here, I'll show you what I'm trying to do. So I have my little circuit down here. Now let's see. I'll go to Google and I'll see how to print circuit paintline, right? This is my experience as a user. All right, there's a blog post. First thing that comes up on Google. You know, I'll click the next ones because these are all old. Okay, how do I print? This is recent. This is a few months ago. So we have our circuit here. Okay. So I see drawer equals QML.draw. Watch as it's going to work, and I was actually just not following the documentation. So let's see, we have draw equals QML.draw draw QFT int var of 0 and in cubits we'll do 4. Okay, it does work. Sometimes it's very annoying though. I've had a lot of problems printing circuits. That time it did successfully work. I've used that exact same method before and had a lot of problems with it. So you can see now that it does print the circuit. I just want to check what's going on with it. So we have our basis preparation, Hadamard. Oh, I think I have an idea as to what is going on here. Let me go over. Let me see. I'm just checking different things right now. I can simplify this a little. I don't actually need this 2 times over here. Two to the I minus j. Oh, this should be, that's the problem. I think this will fix it. And it should be a j minus I, not I minus j. All right, let me see. We go back over to here and we do j minus I. There we go. Implement the circuit recursively. Oh, wow, this is, whew, having to implement functions recursively. This is a throwback right here to like when I was just learning like recursion. That was like, there's a famous homework in our data structures class that's always recursive, and everyone always struggles on it because it takes like 30 hours to do. But having to write like recursive functions is something we did all the time in that class, and now I have not thought about recursion extensively in a long time. Wow, recursion. Okay, let's get to it. So we want to do let's think about, okay, well, our base case, right? Every recursive function has a base case. So we say if wire equals n qubits minus 1 qml dot add wires equals 1. And then we can return, because that's we're done with the function. We reached the bottom. Oh, otherwise, we don't actually need an else here. I recognize that. I just like it. Otherwise, we want to say we want to apply Okay, so what do we need to keep track of here? I'm just trying to think of, there's a trivial way to do it that isn't like fully recursive. Where basically you would just say, here, I'll try, I'll say, well, if wire equals, oh, see, but we only have, I'll just say else, I'll just do it the easy way because I'm lazy, and this is already an hour and 20 minutes. Wow. And then we will just, yeah, okay, base case, recursive case. Oh, okay, yeah. I thought there might be a way to do this more recursively, but what you can just do is you can just say, copy this from up here real quick. What you can just do is you can just say, oh, I did not copy it. I did not copy it once again. You can say, yeah, so I was thinking there might be a way to integrate both of these into the recursion, but oh, oopsies. Get that. I should, yeah, so that's pretty straightforward though. I thought there was a way. I was thinking if there would be a way to do it, but this is the sort of trivial way. All right. See, this is where I'm confused because I did QML.QFT and it's not equal to equals. This is so strange because I did this and this is the whole problem I had earlier. So I do not know what is going on with that. But we did it. We finished the, yeah, you can see, yeah, we finished Fourier transform. Oh, that was a long one, but we did it and I did not give up, which is better than last time.